Hey everyone, and welcome. Today, we are opening up a seriously powerful mathematical toolkit. Now, I know what you might be thinking. Formulas, math, ugh. But trust me, these aren't just abstract ideas from a textbook. These are the very tools that scientists, engineers, and business leaders use literally every single day to find order in what looks like total chaos. We're going to learn how to build a clearer picture of the future. So let's dive into the incredible world of probability distributions. So, what's on the docket today? Well, here's our game plan. First, we're going to start with a really simple, concrete prediction problem, just to see why we even need these tools in the first place. Then, we'll get into the toolkit itself, and we'll see it split into two main families. One set of tools is all about counting things, and the other is for measuring them. After that, we're going to meet the master tool, the one distribution that honestly seems to govern so much of our world. And to wrap it all up, we'll zoom out and see how all these pieces fit together to describe and even shape our world by the numbers. It's going to be great.
All right, let's kick things off with a scenario that I bet hits close to home for any store manager or business owner. It's all about trying to understand what your customers are going to do, which, let's be honest, can feel completely and totally random sometimes.
Okay, check this out. Here's our problem. On the surface, it sounds pretty straightforward, right? 3 people walk in. Each one has roughly a 1 in 3 chance of actually buying something. So, what are the odds? What is the actual probability that exactly 2 of them, not 1, not all 3, but precisely 2, end up at the checkout counter? I mean, you could take a wild guess, right? Maybe say 20%? But when you're running a business, a wild guess just doesn't cut it. You need a reliable, systematic way to find the real number. So, how would you even start? Well, you could try to map out every single possible outcome. Let's say a purchase is P and no purchase is N. The first customer could be a P or an N. Okay, easy enough. But then for each of those outcomes, the second customer could also be a P or an N. Now we have 4 branches. And for each of those, the third customer could be a P or an N. You see where this is going? You end up with what's called a tree diagram, and it gets messy fast. You'd have to list out every combination. PPP, PPN, PNP, NPP, and so on. Now just imagine trying to do that for 50 customers. It would be an absolute nightmare of branching paths. There has to be a smarter way.
And that smarter way is exactly where our first set of tools comes into play. These are called discrete distributions, and they are specifically built for situations where the outcomes are countable. Think about it. We're talking about whole numbers here. 0 customers, 1 customer, 2 customers. You can't have 2.5 customers make a purchase, right? There are these clear, distinct, separate values. And that's all discrete really means.
And the absolute perfect tool for our customer problem is called the binomial distribution. Now, before we can use any tool, we've got to make sure it's the right one for the job. So let's check the conditions. First, do we have a fixed number of trials? Yep, 3 customers. Each customer is a trial. Second, does each trial have only 2 possible outcomes? Yes, they either buy something, which in statistics we call a success, or they don't, which is a failure. Third, is the probability of that success constant for each trial? You bet. The problem tells us it's 30% for every single customer. And finally, are the trials independent? Meaning, does one customer's decision affect another's? We'll assume yes. So it's a perfect match. We've found our tool.
Okay, I know this formula might look a little intimidating at first glance, but let's break it down, piece by piece. It's actually really elegant. First, let's look at the PX part. This is just the probability of all our successes happening in a row. We want 2 successes, right? 2 people buying. And the probability of success, P, is 0.30. So this part of the formula is just 0.30 times 0.30, or 0.30 squared. Simple enough. Now for the next part, Q to the n minus x. This is the probability of all our failures. If 2 people buy out of 3, that means 1 person doesn't. The probability of failure, Q, is just 1 minus the probability of success. So 1 minus 0.30 is 0.70. And we only have 1 failure, so it's just 0.70 to the power of 1. Now, if you multiply those 2 things together, 0.30 squared times 0.701, what you get is the probability of one specific sequence happening, like buy, no buy. But here's the crucial part. We don't care about the order. Buy, no buy is also a good outcome for us. That's where the first piece, NCX, comes in. This is the combinations formula, and it answers a simple question. Out of our 3 customers, how many different ways can we choose the 2 who buy something? And the answer is 3. It could be customers 1 and 2, 1 and 3, or 2 and 3. So we take the probability of that one specific sequence, and we multiply it by the 3 different ways it could have happened. And boom, there it is. This is what I love about having the right tool. No more messy tree diagrams, no more manual counting and guessing. We just plug our numbers, n equals 3, x equals 2, p equals 0.3, into the formula, and out pops a clean, precise, and super useful answer. There is an 18.9% chance that exactly 2 of the next 3 customers will buy something. See? That's not just a number anymore. That's a piece of real business intelligence.
But, the binomial distribution has its limits. It really needs that fixed number of trials to work. But what about situations where events just sort of happen? Think about calls arriving at a help desk or maybe emails hitting a server. There's no fixed number of trials there. For this kind of problem, we need to reach for a different tool in our kit, the Poisson distribution. It is absolutely perfect for counting the number of events that happen over a continuous interval, like an hour of time or maybe a square meter of space.
And believe me, once you know what to look for, you start seeing the Poisson distribution working quietly in the background absolutely everywhere. It's what helps traffic engineers figure out the right number of toll booths to have open during rush hour to stop everything from grinding to a halt. In a factory, it's used to predict the number of tiny defects in a giant roll of steel, which determines if it passes quality control. It's even how your bank decides how many tellers to have on staff during the lunchtime rush. At its heart, this distribution is the invisible engine that makes so much of modern logistics and operations possible.
The real beauty of the Poisson formula is that it all revolves around one single key number, and that number is lambda, the Greek letter lambda. Lambda is simply the average number of events that you already know happens in that interval. That's it. If you know from history that on average 5 customers arrive at your bank every 10 minutes, then your lambda is 5. The rest of the formula uses some cool mathematical constants to do the heavy lifting for you. You've got E, which is Euler's number. It's a fundamental constant kind of like pi, but it's related to processes of continuous growth. Then you have x factorial, which is x factorial. This just means you multiply that number by every whole number below it, and it helps scale the probability correctly for the specific outcome you're looking for. So what this formula lets you do, which is amazing, is take a simple historical average and turn it into an incredibly powerful predictive tool for a specific moment in the future.
Okay, let's hit pause for a second and switch gears. So far, all of our tools have been about counting things, discrete, whole number events. But of course, not everything in the world can be counted like that. Some things have to be measured on a continuous scale, things like time or weight or temperature. And for these, we need a whole new class of tools.
And this slide right here lays out that key difference perfectly. It's really how many versus how much. Discrete distributions have clear gaps between the values. You can have 2 defects or 3 defects, but you can't have 2.5 defects. Continuous distributions, on the other hand, are all about measurement. For something like the time it takes to complete a task, the answer could be 10 minutes, or 10.1 minutes, or 10.113 minutes. Any value within a range is theoretically possible, and you're only limited by how precise your measuring tool is.
Our first tool for measuring things is the simplest one, and it's called the uniform distribution. The name pretty much says it all. Every single outcome within a specific range is equally or uniformly likely to happen. So imagine a computer process that always takes somewhere between 2 and 4 seconds to complete. If it follows a uniform distribution, the chance of it taking 2.1 seconds is exactly the same as the chance of it taking 3.5 seconds, or any other value in that range. It gets called the rectangular distribution because if you were to draw a graph of it, the probability would just be a flat horizontal line, forming a perfect rectangle. This idea of pure, bounded randomness is actually the foundation for almost every computer simulation and random number generator out there.
Now we come to a really fascinating and incredibly useful tool, the exponential distribution. This one is different. It doesn't count the events themselves, and it doesn't measure a value in isolation. What it does is it specifically measures the amount of time between 2 consecutive events. It's the tool you use to answer questions like, what's the probability that I'll have to wait more than 5 minutes for the next bus to arrive? Or, what are the odds that this new hard drive will last for at least 50,000 hours before it fails?
And this right here, this is the light bulb moment. This quote brilliantly illustrates that the Poisson and the exponential distributions are actually 2 sides of the very same coin. They're describing the same random process, just from different angles. So let's say we use the Poisson distribution and find out that, on average, 10 cars arrive at a drive-thru every hour. That's the count. The flip side of that is the time between those arrivals. The exponential distribution would then tell us that the average waiting time between each car is 1/10 of an hour, or 6 minutes. You see? One counts the events happening in an interval, the other times the gap between them. It's a beautiful relationship.
So we've seen all these specialized tools, right? Some for counting, some for measuring. But there's one distribution that is so fundamental, so common, and so incredibly powerful that it really stands in a class all by itself. It just emerges naturally from so many different processes that it truly is the master tool in our predictors toolkit.
I can pretty much guarantee you've seen its shape before, even if you didn't know its proper name. We are, of course, talking about the normal distribution.
You probably know it as the bell curve, and it's called the father of all distributions for a really profound reason. So many things in our natural world, from the heights of people in a population, to test scores in a classroom, to tiny measurement errors in a science lab, they all tend to naturally follow this same pattern. But why? Well, the reason is this powerful, almost magical idea in statistics called the central limit theorem. It basically says that if you take almost any random process, it doesn't matter what it is, and you sample it a bunch of times and take the average of those samples, the distribution of those averages will naturally start to form a perfect bell curve. It's like a kind of mathematical gravity, pulling all this randomness toward this one universal shape. And the most amazing part is that this entire iconic shape is defined by just two numbers: the mean, which is the average value that sits right at the peak of the curve, and the standard deviation, which just tells you how spread out the data is, whether you have a tall, narrow spike or a wide, gentle hill.
So, we've unboxed this entire toolkit of mathematical predictors. We've talked about all these different distributions. But why does any of this really matter? Because whether we can see them or not, these distributions are constantly at work, providing the hidden structure for the world all around us.
Just look at how these abstract concepts translate into real-world dollars and cents decisions. That binomial distribution, it's used on assembly lines for simple pass-fail quality checks every single day. The Poisson, it's helping managers use historical data to decide exactly how many cashiers they need to have working during the busiest hours. The exponential distribution helps engineers predict the failure rate and lifespan of a microchip, which is pretty crucial for setting warranties. Uniform distributions are the engines that power the simulations that test everything from new medicines to airplane designs. And the normal distribution, well, it's the absolute bedrock of modern finance for modeling stock returns and the foundation of all scientific analysis. This isn't just theory, this is practice.
So I think the crucial takeaway here is this. What often looks to us like pure, unpredictable chaos actually has an underlying structure. Randomness follows rules, and when we have the right tools, the right distributions from our toolkit, we can understand that structure, we can model it, and we can make remarkably accurate predictions about the future. So my question to you is, after seeing all this, what parts of your daily life will you now see differently, knowing they might just be following the secret logic of a bell curve or a Poisson process?